Welcome back to an Introduction to Real Analysis. We're now in Chapter 6, Section 2, which deals with interchanging limits. So a lot of analysis has to do with the question of when two different limits can be interchanged. So if you have two different limits being taken, for example, limit 1 of limit 2 of some expression, you can't always just swap the order. For example, consider the quantity n over n plus k. Now, if first you take the limit as k goes to infinity, since n is fixed, this is 0, and the limit as n goes to infinity of 0 is 0. On the other hand, if first you take the limit as n goes to infinity, then this quantity goes to 1, and the limit as k goes to infinity of 1 would just be 1. 1, of course, is not equal to 0. So when talking about sequences of functions, interchanging of limits comes up a lot, and we want to know when they will be the same. So we're going to look at a few different instances of this: continuity of the limit, integrals of limits and derivatives of limits, and convergence of power series. So first, let's talk about continuity of the limit. Suppose you have functions f sub n, and they're all continuous, and they're converging to a function f. Does that limiting function f have to be continuous? Now, we've already seen no, it doesn't have to be. Here's an example from an earlier section. F sub n equals x to the 2n on the interval from -1 to 1. Now, each of those is a polynomial and therefore continuous everywhere. However, the limit on that interval is 1 at the endpoints but 0 everywhere in between, which is definitely not continuous on the interval from -1 to 1, including the endpoints. So continuous functions can be converging to something that isn't continuous. What we want to do is come up with some sort of stricter condition under which, under the assumption that x sub k is converging to x, so here we would take the limit as k goes to infinity of f of xk. Now we want f to be continuous, okay, but f is the limit as n goes to infinity of fn. Now, is that or is that not the same thing as swapping the order of these two limits? Instead of first taking the limit as n goes to infinity and then k, first take the limit as k goes to infinity and then n. We don't know if this equality holds. Okay, but here, since fn is continuous and xk is approaching x, inside the parentheses you would just get fn of x, and of course fn of x as n goes to infinity just converges to f of x. So we want to know when these things would be equal, in other words, if f is continuous. So here's example 6.2.1. Let fn be defined by 1 minus nx between 0 and 1 over n, and then 0 from 1 over n to 1. I've included equality on both here because they'll both be equal to 0. So you simply join this line segment with this one. Now that is a continuous function all the way from 0 to 1, including at the endpoints. However, what does fn converge to? Now as n gets bigger, this point slides left. And so what we see is that everywhere except the left endpoint, we are converging to 0. It will eventually be constantly 0. However, at 1, you are always at a height of 1. So what does this converge to? A function that just has a discontinuity going from 1 to 0. Okay, so the pointwise limit is not continuous at that left endpoint. Now here's theorem 622. Suppose you have a set S, which is your domain. Let Fn be a sequence of functions mapping S into the reals, converging uniformly to F. Then F is continuous. This is the big sort of initial theorem here. If you have continuous functions converging uniformly to its limit, then the limiting function must be continuous. Okay, so let's go ahead and prove that. Let X be in the domain. Let Xn be a sequence in the domain converging to X. We want to show that f of xn is converging to f of x. So let epsilon be positive. Now since the fk's converge uniformly to f, we're going to take advantage of that definition. We can find a k so that the distance between fk of y and f of y is less than epsilon over 3, and that holds everywhere in the domain. Here we're using uniform convergence. Now, since fk is continuous at x, we're also going to fix an index n, so that past that point, we get fk of xm minus fk of x is also less than epsilon over 3. Okay, so this estimate came from uniform continuity, and it holds everywhere. Here we're specifically using the fact that fk is continuous to say that since xm is converging to x, fk of xm is converging to fk of x, so eventually we'll have this being less than epsilon over 3. Okay, so we have this and that already established. Now, if you look at those large indices m, what can you say? The distance from f of xm to f of x, we're going to interpose this fk of xm and this fk of x, and now we're going to hit it with a triangle inequality and get these three different terms. So this first one just uses the fact that fk is converging uniformly to f, so it doesn't matter what this point is, this gap is less than epsilon over 3. Here we also use continuity of fk to say xm is converging to x. Therefore, this is less than epsilon over 3. And finally, again, use the fact that the fk's are converging to f uniformly, so this gap is less than epsilon over 3. Altogether, we have less than epsilon. So f of xm must converge to f of x. In other words, f is continuous at x, and that was an arbitrary point in the domain S. So again, continuous functions converging pointwise to a limit doesn't have to be continuous, but converging uniformly, we have just proved, does. Now, if we just require pointwise convergence, the integral of a limit of functions doesn't have to be the same thing as the limit of the integrals. In other words, it's possible that if the fn's are converging to f, the integral of the limit might not be equal to the limit of the integrals. So let's start with an example to demonstrate that this might fail. First up, example 623. Define fn to be, this is very similar to an example we used before, except now, instead of going from a height of 1 down to 0 at 1 over n, we go from a height of n. So as n increases, this point is sliding closer to 0, but this height is also going up. Okay, so at the left endpoint, we need to give it a value, and we don't want it to go off to infinity, so we're just going to fix the left endpoint to be 0. However, between 0 and 1 over n, we make this line segment going from a height of n down to a height of 0. And then past x equals 1 over n, we just have a flat line of 0. Now, this converges to 0 everywhere pointwise. We fixed this left endpoint to always be 0. Anything to the right of 0 will eventually be cut off by this 1 over n, and you'll just have this flat line covering that point for all sufficiently large index. So what is the limiting function pointwise? The constant function 0. But here was our function fn. What is the integral of fn? Now, since fn is 0 past the value 1 over n, we can cut this integral off at 1 over n. This is just n minus n squared x. We're just going to apply the fundamental theorem of calculus. Integrate this to nx, this to nx squared over 2. Plug in the endpoints of 1 over n and 0, and it all works out to be 1/2. In other words, regardless of n, this integral is always 1/2. We're exploiting here the fact that while the triangle shape was getting very narrow, it was also getting very tall. So the area of the triangle is always 1/2. So the limit of the integrals, well, each integral is just 1/2. What's the limit of 1/2? It's a half. On the other hand, the limiting function here was the constant 0, which integrates to 0. So here we have an example that the limit of the integrals might not be equal to the integral of the limit. So let's establish a theorem to cover when the limit of an integral will be the integral of the limiting function. And again, it looks very much like the previous theorem. Suppose fn is a sequence of integrable functions on an interval from a to b, converging uniformly to its limiting function f, then not only is the limiting function f Riemann integrable, but the integral of the limit is the limit of the integrals. As always, we do in fact have to prove it. So let epsilon be positive. The fn's are converging uniformly to f. So for any positive number past a certain index, we can make the distance between fn and f less than whatever positive number we pick. We're going to pick epsilon over 2 times b minus a. So for all indices sufficiently large, for every x in the interval from a to b, we have this distance. Now each fn is integrable, therefore each fn is bounded. Applying the reverse triangle inequality, we would see that this is bigger than the absolute value of fn minus the absolute value of f, from which you can move some terms around and get this right here. So the absolute value of f of x is definitely less than the absolute value of fn plus epsilon over 2 times b minus a. And from here we conclude that the limiting function f is bounded. So now that we've just established as a baseline that f is bounded, we can attempt to compute the upper and lower integrals of f. Incidentally, you may be objecting that this n we haven't controlled, but it really doesn't matter. For any particular n, this absolute value is bounded above because fn is bounded, so the absolute value of f is less than some fixed constant. All right, so let's compute the upper and lower integrals of f. Now, the first thing we do is this silly algebra trick, right? F is simply f minus fn plus fn. Recall this proposition, the upper integral of a sum is less than or equal to the sum of the two upper integrals, so we break it apart like this. But remember that fn is integrable, so this upper integral is just an integral. Okay, so what do we have so far? The upper integral of f is less than or equal to this upper integral plus this fixed quantity. But now, you similarly compute that the lower integral is bigger than or equal to this plus that. Great. But now we take the difference of the upper minus the lower. These terms cancel out, and we see that the upper integral minus the lower integral is less than or equal to the upper integral of the difference minus the lower integral of the difference. So that's what we have, right? The difference between the upper and lower integral of f is no larger than the difference between the upper and lower integral of f minus fn. But when n was sufficiently large, fn minus f was no bigger than epsilon over 2 times b minus a. So whatever is going on in here, once n is large enough, this function in parentheses is bounded both above and below by plus or minus epsilon over 2 times b minus a. Now that we have a bound on that function, the lower integral is bigger than or equal to, and the upper integral is less than or equal to, plus or minus epsilon over 2 times b minus a times b minus a, in which case we now find that the upper integral is no bigger than epsilon over 2, and the lower integral is bigger than or equal to minus epsilon over 2. So combining the two, we now have that the difference between the upper and lower integrals is less than or equal to epsilon. Epsilon was arbitrary, so if the upper and lower integrals differ by less than epsilon, they must in fact be equal, and therefore f is Riemann integrable. Now that we know f is integrable, let's try to compute the value of the integral. Now, as it turns out, computing the value of the integral is pretty straightforward now that we know it has a value to begin with. So, for sufficiently large index, we still know that the difference between fn and f across the entire interval is no larger than epsilon over 2 times b minus a. So, let's take the absolute value of this difference, in other words, the absolute value of the integral of this difference. Recall this old result. If you have a function whose absolute value is bounded above by m, then the absolute value of the integral is no larger than m times the length of the interval. This parenthetical term is bounded above an absolute value by epsilon over 2 times b minus a. So this integral is no larger than epsilon over 2, which is definitely less than epsilon. So this term changes value as n goes to infinity, but as n goes to infinity, eventually this distance is less than epsilon, so these must be converging to whatever number this is. And that's the final claim of theorem 6.2.4. Let's take a look at an example. The function sine of x squared has no closed form antiderivative. Therefore, if you want to integrate from 0 to 1 this function, now integrating 0 to 1 the function x is no problem. N is a constant, so basically you're trying to integrate sine of x squared, but there is no closed form antiderivative. We cannot use the fundamental theorem of calculus to evaluate the value of this integral because we can't express an antiderivative of this function in a finite way. So we have previously showed that this function on the interval from 0 to 1 converges uniformly to just the x. Therefore, the sequence of the integrals from 0 to 1 of fn must be converging to the integral from 0 to 1 of that limiting function x, 1/2. So even though we cannot compute the value of any particular of these integrals, we do know that they must be converging to 1/2. Now let's look at an example to express that the pointwise limit of integrable functions does not even have to be integrable. If you replace uniform convergence with pointwise convergence, your limiting function might not even have an integral. Consider the following function. Okay, it only takes two values, 1 and 0. When is it 1? when x can be expressed as a rational number where the denominator is no larger than n. So f sub n only evaluates to 1 on rational numbers with comparatively small denominators. Therefore, in the interval from 0 to 1, for any n, there's only finitely many rational numbers whose denominator is small. Okay, if n is 3, for example, you're only looking at denominators 1, 2, and 3. There's only finitely many of each. So f sub n is equal to 1 finitely many times, and it's equal to 0 everywhere else. So each fn must integrate to 0, because except on a finite set, it is equal to 0 constantly. However, what does this function converge to pointwise? For any rational number, no matter how large the denominator, once n is sufficiently large, q will be less than or equal to n. So at every rational number, this will eventually compute to 1. So what does this function converge to pointwise? It converges pointwise to the Dirichlet function, that is 1 on rationals and 0 on irrationals, and we've already seen that that is not a Riemann integrable function on any interval. Therefore, we have integrable functions converging pointwise to something that is not even integrable. Another example, the pointwise limit of bounded functions doesn't even have to be bounded. So here's our fn. It's 0 up to 1 over n, and then it's 1 over x past that point. So for any positive number, eventually as n goes to infinity, this will not hold. So for any positive x, for large enough values of n, you will simply evaluate to 1 over x. Therefore, as n goes to infinity, everything evaluates to 1 over x except 0 itself, where this will always hold, on the interval from 0 to 1. So your pointwise limit is 0 at 0, but for positive numbers is 1 over x, which is not bounded on the interval from 0 to 1. So pointwise convergence is just not enough to say anything about integrability. You can have bounded functions converging pointwise to something that is unbounded. You can have integrable functions converging pointwise to something that is not integrable. Uniform convergence was really the key in the prior theorem to establish integrability. We have a few results under our belt concerning swapping limits and integrals, so let's look at derivatives. Now, uniform convergence was the key to swap limits with integrals, but it's not enough to swap limits with derivatives unless you also have uniform convergence of the derivatives themselves. In other words, fn could be differentiable functions on an interval ab converging uniformly on ab to f, but f, that limit, might not be differentiable on the interval. Let's take a look at an example. Consider sine of nx over n as our function f sub n. Now on all of r, as n goes to infinity, these converge uniformly to the constant function 0. This is pretty straightforward to see because sine is in between plus or minus 1 and n is going to infinity. So everywhere on the line, this collapses to 0 in a very uniform way. But the derivative of fn is simply cosine of nx. The chain rule, of course, spits out this n, which cancels this one. And now you simply have, as n goes to infinity, a cosine curve going all the way up to 1 and down to minus 1 with higher and higher frequency that is not converging pointwise on any interval, even though the derivative of that limit function was 0. What I mean is the limit function f was 0, its derivative is 0, but the function's derivatives are not converging to 0. Furthermore, fn prime, the cosine of nx, at 0, it's 1 for all n. But the limiting function f, its derivative at 0 is not 1. So you really get this mismatch of what's going on with the derivatives of fn versus the derivative of the limit f. Even though we had uniform convergence of fn and every fn was differentiable, the derivatives themselves were not converging to the derivative of the limit. So we had some sort of failure here. Here's another example. Let fn of x be 1 over 1 plus nx squared. Pointwise convergence here is pretty easy to work out. When x is 0, n is irrelevant, and you simply get 1 as your limit. When x is not 0, however, as n goes to infinity, this positive denominator gets bigger and bigger, and you pointwise converge to 0. So that limiting function f is not continuous at 0. It has that jump. Therefore, it's definitely not differentiable at 0. On the other hand, fn prime, you simply compute it out, is negative 2nx over 1 plus nx squared all squared. That converges to 0 at every x. When x is 0, this numerator is just 0. Otherwise, when x is not 0, you have an n in the numerator, sure, but you basically get an n squared in the denominator, so as n goes to infinity, that will converge pointwise to 0. In other words, what do we have here? We have a sequence of functions converging pointwise to something that isn't even differentiable at 0, but whose derivatives converge pointwise to 0 everywhere. And here are the original functions f. Okay, as n gets bigger, they sort of get pushed down. And here are the derivatives. As n gets bigger, this part is getting pushed down, but close to 0, it's getting pushed up. Okay, so on the left is f, where fn, as n goes to infinity, kind of pushes this down. On the right is fn prime, and as n goes to infinity, this gets pushed down, but this gets blown up close to 0. Okay, so fn are differentiable functions. The derivatives are always converging to 0, but the original functions are converging to something that isn't even differentiable. Now, the exercises from this section contain more examples with kind of similar behavior. There's some sort of convergence happening with fn. There are various properties established for the derivatives, and those properties either do or don't carry over to the pointwise or uniform even limit of what the fn's are doing. In other words, it's pretty difficult to nail down how the derivative of a limit and the limit of a derivative will interact with one another. Now here we're going to present one theorem that does give a way in which a sequence of differentiable functions converges to a function, and the sequence of derivatives converges to the derivative of that limiting function. The theorem we're going to state does not technically need every assumption we're going to make. There is a more general statement that holds, but we're going to throw in a little bit of extra assumptions that really speed up the proof. So here's theorem 6.2.10. Assume all of the following. You have a bounded interval I. Fn's are continuously differentiable on I, which means they are continuous and they have a derivative and the derivative is continuous. There is some point C where Fn of C converges to something. So at least at one point, Fn's are converging pointwise. And the derivatives fn prime are converging uniformly to some other function g. Then the fn's are in fact converging uniformly to a continuously differentiable function f, and the derivative of that limit f is the same g that your derivatives were converging to up here. So observe we need a strong convergence on the derivatives, but very weak convergence on the original, only pointwise convergence at one point. Then we will get that the original functions are converging uniformly, and the function they're converging to has a derivative, which is what the derivatives are converging to. Of course, we have to prove it. So in anticipation of what we are attempting to prove, let's denote f of c to be that pointwise limit at the only place where we know the pointwise limit exists. We don't actually know the function f exists yet, but we do know this value exists, so I'm assigning my new function f to take that correct value at that one point. We don't know what happens with the function f anywhere else. Each fn prime are continuous. There's our first assumption, second assumption, I guess, that the fn's are continuously differentiable, so fn primes are continuous. Therefore, they are integrable. So, by the fundamental theorem of calculus, we can compute the following. Fn of c plus this integral from c to x, well, the integral of fn prime will simply be fn evaluated at x minus fn evaluated at c. The fn's of c cancel, and you simply get fn of x. So at every point x in the interval, fn of x is fn of c plus this integral. Now, f of c is the limit as n goes to infinity of fn of c, and we just established fn of x is fn of c plus this. The fn primes are converging to g uniformly on I. Therefore, they're doing so on the interval from c to x, or x to c, depending on which was bigger or lesser, not a big deal. So what did we just prove about taking limits of integrals and integrals of limits? Since we have uniform convergence of fn prime, we can say that the limit as n goes to infinity of this integral of fn prime is in fact the integral of the limit of fn prime, which was simply g. Therefore, we can define for every point f of x is now defined to be the limit as n goes to infinity of this quantity on the right, which is simply f of c plus this integral of g. So here's how we have defined our function f of x. It is f of c plus the integral from c to x of g, where g is that uniform limit of the fn primes. The fn primes are continuous and converging uniformly to g, therefore g is continuous. In other words, g is integrable. So from the fundamental theorem, we can see now that f is differentiable on I. We have a constant f of c plus an integral of a continuous function. And from the fundamental theorem, if you take a derivative of this, everything works out great wherever g is continuous, which is everywhere on I. So the derivative of this constant is 0. The derivative of f is therefore simply g. Great. That was one of the things we wanted to establish. The only remaining claim is to show that the fn's are converging uniformly to f. Okay, we don't actually have that yet. We simply defined f of x to be this. We've now established that it is the derivative of g. We need to show that the fn's are converging to f. So let's just denote a and b to be the infin soup of the interval. We never actually defined what the endpoints of the interval were. Also, I may or may not include its endpoints. Let epsilon be positive. We have pointwise convergence. So we can pick m1 so that for all indices past that point, fn of c minus f of c is less than epsilon over 2. Fn of c is converging to f of c. The fn primes are converging to g uniformly, so we can pick another index past which fn prime and g are within this much of each other everywhere in the interval. Now we just take indices that are big enough for both to hold. So for all sufficiently large indices, everywhere in the interval, this distance is less than this quantity, and at c in particular, this distance is less than epsilon over 2. Here's everything we have. We're now going to compute the distance between f of x and fn of x, again, for such large indices where all of the above inequalities hold. First things first, g is f prime. So to integrate f prime from c to x, you would simply throw the fundamental theorem of calculus at it and get f of x minus f of c. The minus f of c cancels this. In other words, this parenthetical term is simply f of x. Similarly, this integral would be fn of x minus fn of c, cancel the fn of c's. This second parenthetical term is simply fn of x. Now we hit this with the triangle inequality. F of c minus fn of c is our first term. Integral of g minus integral of fn prime is our second. Okay, so the first equality and then this triangle inequality are justified. We're going to leave this first term alone for the moment, and here we simply have one integral minus another, but it's on the same interval, so we combine them into one integral. We know that fn of c is very close to f of c. It's epsilon over 2 close. Similarly, g minus fn prime, that in absolute value is no bigger than epsilon over 2 times b minus a everywhere in the interval, so certainly between c and x. The length from c to x is definitely not larger than b minus a. So you could simply multiply your bound of epsilon over 2 by 2 times b minus a by the absolute value of x minus c, but the absolute value of x minus c is less than b minus a. Those cancel, now you just get your epsilon. Meaning, f of x minus fn of x is less than epsilon everywhere. X itself was not relevant. Therefore, the fn's are converging uniformly to f. Now, in the event that the interval I is unbounded, all of the previous proof works pretty much the same. The only way we used a and b, the sup and inf of the interval, was when we got to proving uniform convergence of fn to f. In other words, if you take all of these assumptions but you remove the fact that I is bounded, you still get this conclusion, except instead of the fn's converging uniformly to f, they are converging pointwise to f. As an example where this can happen, consider fn of x to be just the line, x over n. As n goes to infinity, this is a line of flatter and flatter slopes. So you do converge pointwise to 0 everywhere, but definitely not uniformly. Okay, when x is very, very big, it requires larger ends for this to converge to 0. But it will eventually happen. You do get pointwise convergence to 0, just not uniform. So now we're going to turn our attention to power series. Back in section 2.6, we saw that a power series converges absolutely inside the interval of convergence, possibly not at the endpoints. So it definitely converges pointwise. So let's show that the power series, and in fact all of its derivatives, converge uniformly. This fact will allow us to swap several types of limits by using previously established theorems from this section. Not only is the limit continuous, if we can show that they converge uniformly, but we can also integrate and differentiate convergent power series term by term, which is a wonderfully powerful tool. First up then is proposition 6.2.11. Suppose you have a power series which is convergent, has a radius of convergence rho. We're always going to assume that this radius of convergence is positive, by the way. Then the series must converge uniformly on any interval of the form a plus or minus r, where r is any positive number less than rho. So any closed interval centered at the center of the power series and contained within the interval of convergence, on that interval, including the endpoints, the power series will converge uniformly. Let's get started. Let's denote I to be the open interval a minus rho to a plus rho, if rho is a real number. Otherwise, we're going to let I be all the real numbers. When the radius of convergence is finite, this is typically how we will denote our interval of convergence, with the understanding that when the radius of convergence is infinity, if I write a minus infinity to a plus infinity, we understand that that's going to mean all real numbers. The formality with which we keep these two things separate will get a little muddled later on. A minus rho to a plus rho, if rho is infinity, means all real numbers. But for now, we're writing it quite clearly. So let's let r be a positive number less than rho. Then the series converges absolutely for every x in the interval I, not including the endpoints. This was back proposition 2.6.10. So it definitely converges absolutely at the specific value of a plus r, because remember r was less than rho. Okay, setting x equal to a plus r, here we had x minus a to the n, so x minus a simply becomes r. We now have a pretty straightforward power series. We have this power series which converges. Okay, the power series in question converged absolutely when x was equal to a minus r. So the absolutely explains the appearance of this absolute value around the coefficient Cn. We don't need it around r because r was positive. The terms of this series are non-negative, right? R is a positive number. We have an absolute value on Cn. Since each individual term of the power series is not negative, the partial sums of the power series are not decreasing. Therefore, the tails of the power series are not increasing. If you go from one tail to the next, you remove a single term like this, and you can only go down. You are not increasing. Also, the tails must have limit 0 because the power series converges. So the tails of the power series are decreasing monotonically with limit 0. Therefore, for any epsilon, for sufficiently large index, we have that the tail is less than epsilon. Our power series has tails which are less than epsilon. So now let's let x be somewhere in between a minus r and a plus r. And again, we're going to let m be a sufficiently large index where this tail of this specific series is less than epsilon. Now we just need to compare our power series partial sum going out to m minus the partial sum going out to k. M is larger than k, so what remains are the terms from k plus 1 to m. We can now apply the triangle inequality because we only have finitely many terms, and we end up right here. X belonged to the interval from a minus r to a plus r, so the distance to a is less than r, or perhaps equal to it. And we've already established that this particular finite sum certainly is less than this tail, again, because all of the individual terms are not negative, so going from a finite sum to the complete infinite tail can only add things on, but this tail was less than epsilon. So overall, the mth partial sum minus the kth partial sum is strictly less than epsilon, provided m and k are both past this index m. So here's what we have. There is some cutoff, capital M, so that for any two indices m and k past that point, the difference of the two partial sums is less than epsilon. But that is exactly the definition for a sequence to be uniformly Cauchy. Here is f sub m, here is f sub k. These are our polynomials, the partial sums of the power series. We've just established that the polynomials, the partial sums of the power series, are uniformly Cauchy. Therefore, they converge uniformly by proposition 6.1.13. Also, the partial sums are polynomials, which are continuous. So now we have polynomials, the partial sums, converging uniformly to something. Since the polynomials are continuous and are converging uniformly, their limit must be continuous as well. So not only does a power series converge uniformly inside its radius of convergence, but it is converging to a continuous function. So let's just denote f of x to be this power series. As we just discussed, f of x is continuous on any interval of the form a minus r to a plus r, but r is an arbitrary number less than rho, so you can extend that all the way out to a minus rho, a plus rho. And again, when rho is infinity, this represents the entire real number line. So power series can't help but converge to a continuous function inside the interval of convergence. At the specific endpoints, if they exist, all bets are off. But inside the interval, if a power series is converging at all, it must be converging to something continuous. So now we're going to move on to show that power series can be differentiated and integrated term by term. The differentiated or integrated power series, incidentally, will again be a power series, and we've just shown that when they converge, they cannot help but converge to a continuous function. We're also going to show that the radius of convergence of this derivative or integral series cannot be any smaller than the radius of convergence you started with. Therefore, when you take a derivative, once we show these results that is, when you take a derivative, you end up with a new power series whose radius of convergence didn't get any smaller, and you can keep doing that. So anytime you have a power series that converges, it's not just converging to a continuous function, but to an infinitely differentiable function. First, we have to prove that we can anti-differentiate. As integration only needs uniform limits, this is the easier task to handle. Corollary 6.2.12. Again, let f of x denote our power series with a positive radius of convergence rho. Let I be the interval from a minus rho to a plus rho. Again, if rho is infinity, this is understood to be the entire real number line. Then if we integrate from a to x, our power series f, what we end up getting is a power series whose coefficients are the Cn minus 1 over n, where Cn minus 1 is simply the coefficients of the original power series, but where the index has been shifted by 1, times x minus a to the n. And this new power series has a radius of convergence at least as large as rho, the radius of convergence of the power series we started with. On to the proof. Let r be a positive number which is less than rho. By proposition 6 to 11, the partial sums of f must converge uniformly on this nice closed bounded interval a minus r to a plus r to some function f, the function that the power series is converging to. Alternately, for any x inside this interval a minus r to a plus r, convergence is uniform on the interval from a to x or x to a if x is less than a. Either way, what you end up with, the integral from a to x, since f is the uniform limit of the partial sums, instead of taking the integral of this limit, we can take the limit of the integrals because convergence was uniform. So using theorem 6.2.4, which we've just proved, the integral of the limit is in fact equal to the limit of the integrals. This is now a polynomial. It's a finite sum. How do you integrate a polynomial? Well, to integrate this polynomial, you just have to integrate every term of it because it's a finite sum. There's really nothing to it. What's an antiderivative of constant times s minus a to the n, where our variable is s? Well, s minus a to the n plus 1 over n plus 1, and you have this same coefficient c sub n. So now we've established that the integral from a to x of f is in fact the limit of this sum right here. We need to evaluate this at s equals x and then at s equals a, take the difference. Note that when s is equal to a, you'll simply get 0 everywhere. So the integral from a to x of f is the limit as k goes to infinity of this sum. So we have a new power series. We're taking the limit as k goes to infinity. We want to show that this power series definitely converges. Let's reindex the sum first. Instead of starting at 0 with an n plus 1 here and an n plus 1 there, we're going to let it take this form here where you have an n and an n, where the cost is that the c subscript is now n minus 1, but our sum will start at index 1. Also recall, x in this interval was arbitrary, where r was anything less than rho that was also arbitrary. So since we have convergence on the interval from a to x, where x was arbitrary and r was arbitrary, we definitely have convergence on the entire interval from a minus rho to a plus rho. So the radius of convergence could not have gotten any smaller. All right, example 6.2.12a, a sort of modified version of example 6.2.12 from the text. A power series can be integrated term by term without sacrificing the radius of convergence. So remember this function sine x over x. There's no closed form antiderivative. Most people who are taking a course with this textbook have already dealt with some power series before. So they've already seen a power series for sine x. If this is new to you, go back and derive the Taylor series for sine, and you'll find that this is what you have. It converges on the entire real number line. With this as our power series for sine x, we can now divide by x. All that does is drop a power of x from every term. This is called the sinc function, sine of x over x. We can now integrate the sinc function by integrating the power series term by term. So while we don't have a closed form, a finite sum of terms that represents this, the power series is not too weird. You have this alternating minus 1 to the n. You recover the original power of x from your sine function. You divide it by x that lost a power, then you integrate it, raises it again. What has changed, however, is that this denominator is not 2n plus 1 factorial, it's 2n plus 1 times 2n plus 1 factorial. And here is our antiderivative of sinc x. This antiderivative of sinc is sometimes denoted capital SI of x. Both of these functions are used a lot in signals processing. Sine x over x is like a sine wave, but it gets divided by larger numbers as x gets bigger, so it's a sort of decaying sine wave, and then integrating that or getting sort of area underneath it, that gives you your SI function. The question then becomes, if a power series can be integrated term by term without losing any radius of convergence, does the same hold for derivatives? And in short, the answer is yes, yes it can. Here's a statement of the following corollary, 6.2.13. Suppose you have a power series given as we have typically been writing them with positive radius of convergence rho. Then on the interval from a minus rho to a plus rho, again, when rho is infinity, we understand this to be all real numbers. The derivative is given exactly as you would think. If you take the derivative term by term, you would bring down this power and you would lose one power up here. After reindexing, you get an n plus 1 times cn plus 1 x minus a to the n. In other words, the derivative of a power series is exactly what you would hope. Now we have to prove that. Now, unsurprisingly, we're going to apply the only theorem we've really established regarding convergence of derivatives of a sequence of functions, 6.2.10. So let's let r be a positive number less than rho. Here is I, our nice bounded interval. The partial sums of f are just polynomials. Those are definitely continuously differentiable. The partial sums, remember, are the sequences of functions that are converging to our power series f. So the partial sums are definitely continuously differentiable because they are polynomials. The derivatives of the partial sums can easily be computed because this is just a polynomial. You just compute it term by term. After reindexing, you end up exactly with what we would hope. We have partial sums of the series we're going for. So here is the partial sum of derivatives, or derivative of partial sum, however you like to put it. What we need to verify is that these derivatives of partial sums, these are our fn primes, we need to show that they are converging uniformly to something on G, and that the something they are converging to is exactly the derivative that we want. So let's define this new quantity capital R. It's going to be the lim sup of the absolute value of these coefficients Cn, the nth root of them. So we're taking the nth root of the absolute value of the coefficients and taking a lim sup of that. We have no idea if there's even a limit, just define the lim sup to be R. Here then is the capital R we just defined. The series for f of x is converging, therefore the individual term has to go to 0, therefore the absolute value of the individual term has to go to 0. If it goes to 0, it's eventually less than 1. So the absolute value of Cn times x minus a to the n is eventually less than 1. Taking an nth root and dividing by the absolute value of x minus a, we see that the nth root of Cn is eventually less than 1 over x minus a. X was chosen from the interval a minus rho to a plus rho, which means the biggest, the supremum that x minus a could possibly be is rho. So the Cn to the 1 over n is in fact less than or equal to 1 over rho, meaning the lim sup, this capital R that we've defined, can be no larger than 1 over rho. If rho is infinity, you get a 0 here, it all checks out. But in either case, this R is not infinity. It is 0, or it is a nice finite number, less than or equal to 1 over rho. So capital R is this lim sup that we've defined. It's definitely a finite number. It's less than or equal to 1 over rho, in fact. Now let's let epsilon be positive. Back in example 2.2.14, we established that the limit of n to the 1 over n is 1. Past a certain index, we can guarantee that n to the 1 over n is no larger than 1 plus epsilon. So now let's work through this lengthy computation. This was the definition of R. Cn can only be made bigger by multiplying by n because n is going to infinity, so we get a less than or equal here. N to the 1 over n is less than 1 plus epsilon, so this n to the 1 over n I can pull out as a constant 1 plus epsilon, but now here we just get R again. In other words, R is less than or equal to this lim sup, which is less than or equal to 1 plus epsilon times R. There's the inequality we just derived. But epsilon is arbitrary, so whatever this lim sup is, it's trapped between R and something extremely close to 1 times R, which means it must in fact equal R, as epsilon could be made arbitrarily small. By the root test, we now see that a power series whose coefficients are given here, n times Cn, which is basically the power series we are hoping is f prime. Since this lim sup is R, the radius of convergence is 1 over R, at least 1 over R. But since R was less than or equal to 1 over rho, 1 over R is bigger than or equal to rho. So the power series that we hope is the derivative has radius of convergence at least as large as rho. So after reindexing, that's exactly the power series we end up with. All right, so the power series that we are hoping to establish is equal to f prime has radius of convergence at least rho. Great. Now that we know this series has radius of convergence at least rho, it must converge uniformly on any interval of the form a minus r, a plus r, where r is less than rho. This is the result we established earlier in this section. So the derivatives of the partial sums converge uniformly to the series we claim, and we can now complete the application of theorem 6.2.10, completing the proof of this result. The partial sums of the power series are the sequence of functions that we want. They converge at a single point. They converge at a. The interval I was bounded. It was of the form a minus r to a plus r, where r was arbitrary up to rho. The derivatives of the partial sums converge uniformly to this, which is going to now be the derivative of the thing that it was converging to, and there's theorem 6.2.10 in action. So the net result is that a power series can be differentiated term by term inside the interval of convergence. Since power series can both be integrated and differentiated term by term as long as you're inside the interval of convergence, incidentally, at the endpoints, some weird stuff can happen, but you generally ignore those. But this flexibility makes power series really, really useful in the study of differential equations. Also, if you're talking about complex valued functions, very little changes here. So power series become one of, if not the, default presentation for complex differentiable, which is also known as a holomorphic function. Holomorphic or complex differentiable functions, it is very useful to just think of them as power series. That is what they are. That's how they behave. You integrate and differentiate term by term, and it all works out as long as you are inside the radius of convergence. Let's take a look at example 6.2.14. Here is a function we define as a power series. You can check that it converges everywhere. Okay, just apply the ratio test, for example. Furthermore, f of 0 is definitely 1. Every term vanishes except for index 0, and we always understand in power series that when you get a 0 to the 0 at the index 0 term, that's always 1. So differentiating term by term, you will bring down an n in every term, but it will cancel one here, and now you will have x to a power over that factorial. You have exactly the series you started with, so this is a function that is its own derivative. So after section 6.3, we'll see that being able to define a function and find that it is its own derivative and knowing how it evaluates at a single point, in other words, f of 0 equals 1, is a very straightforward way to define what the exponential function is. We defined the exponential function back in section 5.4 in a very roundabout way. We took the function 1 over x, we integrated it with a base point of 1, we called that a logarithm, we found that was invertible, and we defined the inverse of this logarithm to be the exponential function. And it's a pretty simple way to build up your exponential and logarithmic functions, but it feels a little weird. This is a way to define a function that is its own derivative and define that to be the exponential function. Incidentally, if you're interested in more straightforwardly defining an exponential function as something like raised to a power and then trying to compute its derivative according to the raw definition of the derivative, it is doable, but it's weird and it's actually strikingly difficult compared to these other presentations. Example 6.2.15. Let's look at the following power series. It's very similar to the one we have before, except there's no factorial down below, and it's being multiplied by n. So I guess it's not the same at all. Now we already know that x to the n, if you add that up, you have your geometric series converging to 1 over 1 minus x, at least with a radius of convergence equal to 1, centered at 0. Now term by term differentiation of x to the n will give us this n plus 1 times x to the n, and the derivative of 1 over 1 minus x is 1 over 1 minus x squared. We can now multiply by x so that the coefficient matches the power, and we get x over 1 minus x squared. We now have a coefficient times x to that power starting at index 0. We can re-index this to start at index 1 and just get n times x to the n, but notice, of course, if you include the 0 term, you've got a 0 times something. In other words, this series is actually the same as this one. You have exactly the same terms in it, meaning that the function that we started with, this right here, is just x times the derivative of 1 over 1 minus x, which is just now x over 1 minus x squared. We've derived a power series for the function x over 1 minus x squared. This is a pretty typical presentation. A lot of students see this in the first time they work with power series. You just sort of recognize that 1 over 1 minus x is a power series you know. Take a derivative of that will give you this here, multiply by x, and that's how you end up computing this power series for that function. Let's review everything we've talked about. Interchanging limits is always tricky. Whenever you take a limit and then you take a limit of that, never take that operation lightly. Can you do the limits in that order? Can you do it in the other order? How important is it? This is always a big question. When continuous functions converge uniformly to some other function, the resulting limiting function is continuous. Remember that continuity is a definition that inherently involves limits. So if you have a limit of continuous functions, you are essentially dealing with a limit of a limit. And we have shown that when you have uniform convergence of those continuous functions, the resulting function must be continuous. Also, when a sequence of integrable functions converges uniformly, the result is integrable. When a sequence of differentiable functions has their derivatives converging uniformly, also this other little assumption that the original functions converge pointwise at least once, the resulting limit is differentiable. And these are our raw theorems to say that the integral of a limit is the limit of an integral, and the derivative of a limit is the limit of the derivatives. We then applied all of this stuff to power series to prove some nice results, to build a nice little toolbox to justify why power series are honestly so useful and so straightforward to work with inside their radius of convergence.